that you use. It's a substitution with a lookup table. I'll go into detail each one of these steps. This is just kind of an overview. And then it goes into shift rows, which is transposition, and then mixes and combines all of the data. And then it'll add a round key. The final round does not mix the columns. Okay, the first one is subbytes, and it uses linear substitution. Basically, what it's doing is going to make up the lookup table. It's just going to basically copy this stuff over. And then it's going to actually shift the rows. As you can see by the numbers, it just shifts it one row over. And then you go into the mixed columns. Use the fixed polynomial as seen in XOR, which it'll help that transform it. And it's going to add the round key. Now, it's going to take from the state, it's going to take the block, and then from the key, it'll take that and XOR those two. And then finally, that'll be added into the lookup table with the round key. And an implementation for this, if you want some source code to do with this, I have this site listed here, and I'll put this up on my website, and I'll have the address for that stuff at the end. But this code is BSD licensed, and it includes a Visual Studio workspace and source code with assembly source code if you want that too, as well as a Windows DLL if you ever want to do Windows stuff with it. The next one is RSA. It is asymmetric, meaning it's public key, and it was the first cipher for signing and encryption. And this is kind of confusing, this part here. It was first described in 1973 by Clifford Cox of the GCHQ. But in 1977, Ron Rivest, Adi Shamir, and Len Alderman described it too. Now, we didn't know about the Clifford Cox one in 1973 because he was working for the British government at the time. And while he was working on it, it was classified information, so he didn't actually get the claim to fame for this one. And this is sort of how RSA works. You'll take, and it uses prime numbers, because prime numbers are sometimes very hard to calculate unless you have a lot of computing power. Okay, this is first how it works.
Prime numbers are hard to calculate.
Well, I'll get back to you on that. I mean, I don't know the general like math of how people know math, so I'll just get back to you on that. Yeah.
Well, just to give a quick answer to this question.
Okay.
It's not the numbers themselves that are hard to calculate, but what you're looking for is multiplying two numbers together is really, really easy, but figuring out the factors of a number is really, really hard. And that's sort of the premise behind RSA. That's the hard part to calculate, factoring.
In fact, it just takes more math than the actual factors and
Well, it takes a lot longer. There's sort of, it's
no easy way to
yeah.
that
There's
only
no
possible that many times. So if it's a number like 5,000, you're going to have at least 2,500 tries.
So the computer just takes more calculations per second to actually.
Yeah. I guess I should say I'm not an expert at this stuff. I'm learning this stuff as a hobby and stuff, and I'd just like to show some people like what you can do and stuff. Okay, this is how RSA works. The first prime number that you calculate, we'll call it P. And you're either going to keep this secret or you're just going to delete it. Now, if you delete it, you want to make sure you delete it securely and not just throw it off somewhere. Your second prime, we're going to call that Q, and we're going to keep that secret or delete it securely again. And for n, we're going to take p times q, which is your modulus, and that's going to be public. So people can see that if they need to. Now e is going to be public exponent, which again, public, people can see, doesn't matter. And d is going to be your private exponent. Again, private, get rid of securely. Now your public key is actually E and N, and your private key is D. Now to encrypt M, which is your plain text, you're going to take M to the power of E mod N, which will give you M to the power of 17 mod 3233. And to decrypt, it's basically reverse of that stuff there. And on the bottom, you can see the examples, just if you want to encrypt simple numbers. RSA needs to use padding schemes. Otherwise, it'll be too easy to calculate the numbers. You got to throw in some stuff to, like, take people away from the actual numbers that you want to calculate. Because if you have M, as in M on that page, as 0 or 1, your output will always be 0 or 1. And that will easily give it away unless you use some kind of padding. And low exponents may be less than your modulus. And if you use low exponents, that'll be too easy to decrypt. So that you don't want to use low exponents. You got to make sure you have high exponents. So computing power is definitely preferred with this. And for digital signing, it's quite easy. You just take a hash, and you can use anything for that, any kind of hashing you want to do, if you want to make your own. And take that to the power of D, your private exponent, and mod N, which will give you X. I take X to the power of E mod N should give you the hash. If it doesn't, then you know it's been tampered with. Now, Blowfish is my favorite because in 1993, Bruce Schneier made it, and he made it public domain, which is very cool with all of these. It has a block size of 64 bits and a key size from 32 to 448 bits. And again, it has a Feistel structure, like seen before, with 16 rounds. And you can see the implementation on Bruce Schneier's website. He has plenty of source code links. I know there was C, C++, there was Python, Perl. I think there was even COBOL up there. I don't know how they did that. And that's basically how Blowfish works. What it'll do is it'll split it up into 8 bits and throw those into an S box, or substitution. It'll substitute the stuff. And then they'll use modular addition from the output of those S boxes, and then it'll go into modular addition with all 4 of those S boxes. And it'll do this for each part of the message. And then that'll give you your output with all the modular addition parts there. RC5, there are plenty of RC codes. RC stands for Rives cipher, or Ron's code, as Ron Rives made it. It was first published in 1994. Has a block size of 32, 64, or 128 bits. The key size up to 2040 bits. Again, it has a Feistel structure with 12 rounds. And RC5 and RC6 are both proprietary for RSA security, so source code documentation is not as good as you would want it to be. Again, it's a block cipher, same with RC5. However, RC6 was made by Ron Rives. Let's see, I think it was Matt Robshaw. Okay, I forget their full names. Block size of 128-bit, key sizes of 128-bit, 192, or 256-bit. Now, one-time pads, they're very simple to implement, and I don't know how many of you know about one-time pads, but computers don't use like pens and papers and stuff, and that's how this stuff is mainly implemented. And basically, you need a pad. So what you'll do is take, say, a Scrabble bag with all the numbers and letters, and you'll take out the letters and write them down on a pad for how many you need on your message. Say your message is hello. So you only take out that many number or more if you need more. And see, it has to have the same length at least, otherwise there's no point. Now the drawbacks to this is you have to have it completely random. If it's not random, then it'll be easily brute forced. And again, you need secure exchange of the pad. If you don't have secure exchange and somebody looks at the numbers that you picked out, what good is it going to do? And it's one-time use. I mean, you can't reuse the same numbers or letters that you used in the first part. Otherwise, you know, it's not gonna be any use. And that goes into integrity. Now, if one-time pads, the integrity deals with all of the secure exchange and the secure generation of the letters and numbers. Make sure all that stuff is secure so no one sees this stuff. And these are simple how to do this stuff. So we're going to take hello, and we're going to give a numerical value to each letter in the alphabet, starting with 0. And then say we take out 5 letters from a Scrabble bag, and we get J-E-P-S-W. What we're going to do is take the numerical values of hello and J-E-P-S-W, and we're going to add those together. Now you might think, well, 11 plus 15 is more than 25. So what you do is you just come back and start at the beginning and keep going, which gives us then QIADJ. That's how you encrypt the stuff. Now to decrypt it, it's basically the reverse. Where we were adding to encrypt, we're just going to subtract the letters. So see, again, when you subtract them, they might not come out to the end, so you just got to go back to the alphabet and keep going. Just got to go through it, and that should give you hello. Very simple. And I just wanted to cover it because it is a very basic way to do stuff, and it's very unbreakable as long as you don't have, you know, the same stuff over and over again. Now the legalities. This kind of surprised me a bit. There are no U.S. import laws, thankfully. However, the U.S. did sign the Wassenaar Agreement, and this agreement is really long, so I did not even bother to read most of it. However, they do have something in there called the General Software Note. It was in December 1998, I believe, and it says software is not included as restricted technology if it is generally available to the public, such as, you know, if you make something and you give out the source code, then that's generally available. However, if your code is or was made before 1998, then it does not fall into this category. So you can't export it then. And however, there is a lot more laws than just what I've described. So if you want more information on that, the two websites here, the first one is this guy, Bert Coops, is his PhD website. He went through almost, I don't want to say every country, but a giant list of countries, and actually got the laws for each country. And it's huge. It's a